the unit vector is any vector whose length is equal to 1. For example, this might be I or j with the following components. If you find the length of the I, this is going to be square root of 1 squared plus 0 squared plus 0 squared, which is equal to 1. The same for the j. The length of the j is equal to 1. But they are not the only unit vectors. And even more, we can create the unit vectors from any vector. So let's say we're given some vector v with the components 1 and 1. So in 2D, this is going to be the vector which looks like this, with the components 1 and 1. So what I want is, I would like to build on the top of this vector v another vector u, so that it is going to have the same direction, but its length is equal to 1. So the length of the u, this is going to be equal to 1. So in order to do this, so you see, so the vector v and vector u, the u is shorter than the v, right? And u can be obtained by multiplying the v to some constant, right? By scaling the v, by making this shorter, we can obtain the u. Now, if these two vectors are equal, then their length should be equal as well, right? So if I find the length of the u, it should be equal to the length of the kv, right? And we know that the v, the vector which we're going to build, is going to have the length to be equal to 1, so this is equal to 1, and this part can be written as a model of the k multiplied to the v, right? So I'm writing the k in the model because it should be a positive number. From here we can find the k, this is going to be equal to 1 over the norm of the v. So basically, if you multiply the v vector to its norm, to the reciprocal to its norm, we're going to obtain the unit vector. Basically, let's consider an example for this case. So if the v is given with the components 1 and 1, the norm of the vector v is going to be equal to 1 and a square plus 1 and a square from the square root, or basically square root of 2. Then the vector u is obtained by multiplying 1 over square root of 2 to the vector v, and this is going to be equal to 1 divided to the square root of 2, 1 divided to the square root of 2. So now we are going to define the standard basis vectors. So in 3D, in R3, I was the components 1, 0, 0, j was the components 0, 1, 0, and k was the components 0, 0, 1, are called the standard basis vectors. So they are called the standard basis vectors because we can express any vector in R3 using them. For example, let u is any vector in R3 with the components u1, u2, and u3. And we can express this using ijk. So where the components of this vector are the scalars, are just the constants, and you can write this down as the u1 constant multiplied to the I, plus u2 constant multiplied to the j, plus u3 constant multiplied to the k. For example, if the u is given with the components t, 1, and minus 3, we can write this as a ti plus j minus 3k, where this plus and minus are not the addition of the j to the ti, or are not a subtraction of the 3k from the j. They are just denoting the signs of the components of the vectors. So this plus means that the second component of the vector is positive, plus, and this minus means that the third component of the vector is negative, minus. So indeed this is equal to this one, so I would like to show that this is equal to this one by substituting the t, I was the 1, 0, 0, by substituting the j was the 0, 1, 0, and by substituting the k was the 0, 0, 1, and by adding the vectors we're going to obtain the original vector. So if you multiply a constant as a vector, it means that you're going to multiply to all the components of the vector to this constant, plus 0, 1, 0, plus 0, 0, minus 3. So when we add 3 vectors, we need to add them component-wise, right? So every first components, we're going to add them and write them as a first component. Every second component, we're going to add them and write them as a second component. And all the third components are going to add it, and we can write them as a third component, and we're going to get exactly the year. So basically, we can express any vector in 3D using the basis vectors. So now, if we're given a t vectors, which are expressed in terms of the basis vectors, for example, t I plus j minus 3k, and another vector v, which is also given in terms of the basis vectors, for example, 4i minus 5k. We can do the operations with the vectors only with them. For example, if I need to multiply the vector u to the t and add this to the 3 multiplied to the v, what I'm going to do is I'm going to multiply the 2 to all these 3 components of the vectors. So this is going to be equal to the 4i plus tj minus 6k, and if I need to multiply the 3 to the v, I'm going to multiply the 3 to all the 3 components of this vector. This is going to be plus 12i. So there is no j component, right? It means that the second component of the vector is equal to the 0. So basically it is written here plus 0 multiplied to the j, right? So plus again, so if you multiply the 0 to the j, it's going to be again 0, right? And if you multiply the 3 to the 5k, it's going to be minus 15k. So when we added t vectors, so with this t components, we need to add again the corresponding components separately. So I was the I, j was the j, and k was the k. So 12i plus 4i is going to be 16i. So 2j was, there is no j, so that is why it's going to be simply 2j. And minus 6k plus minus 15k, it's going to be minus 21k. So the vector 2u plus 3v can be written as 16i plus 2j minus 21k, or with a 3 tuple we can write this as 16t minus 21.